Intermolecular forces are the forces behind the phenomenon of surface tension and of viscosity. If we didn't have intermolecular forces, everything would be a gas. And what we see in liquids is surface tension and viscosity. These are the results of intermolecular attractions. If you are careful, you can actually float a paperclip on water. The container needs to be very clean and the water needs to be fairly pure, but you can float a paperclip on the surface of the water. If you've ever gone to a river or a lake or a stream, you may have seen water bugs, water skaters. And they're these little bugs, and they skate on the water. Is that because they're less dense than the water? Are they floating? No. There's actually kind of a skin on the water. I don't know if you can see it. It's a little hard to see. Do you see how this, the side of this container looks like it's bent here and over here? That's because the water is actually bending down. It's almost like you took a sheet of plastic and set it over, maybe a piece of saran wrap, and set it over the surface of the water and put the paper clip on it. And it's going to bulge down a little bit, but it's not going to break through and fall. Paper clips are made out of metal. Metal is more dense than water. It should sink, right? It should sink, but it doesn't. That's surface tension. So what's going on with that? Well, here's an illustration of water. Down here, we have interior molecules, and these are going to have forces of attraction with all of their neighbors. But the surface molecules don't have anybody above them to interact with. They only interact with the ones next to them and below them. This results in a net inward pull on these molecules. And it kind of forms a skin. And this is why water forms spherical droplets as it falls, is because it's trying to minimize the surface area. So it forms this skin, this inward force between the surface molecules. There's a tension there at the surface, and it resists penetration. So you can lay a paper clip or a needle sideways on top of the surface of the water, and it will float. If you look at droplets of water, here's a droplet of water hanging off what looks like maybe a blade of grass or something. And it's not a perfect sphere, is it? Because gravity is pulling it down. It's sticking to the grass, it's pulling down. In space, here's some astronauts having a little fun on the space shuttle with a ginormous drop of water. No gravity. The water forms a sphere and just floats along. And if you break it into smaller pieces and herd them together, they'll join up and you can make a really big sphere of water just floating. Because of the surface tension, it's going to form a shape that has the smallest amount of surface area, which is a sphere. Viscosity is another thing that is due to intermolecular forces. One way to define viscosity is resistance of a liquid to flow. And the place I hear this most in everyday life is in TV commercials for motor oil. And they talk about viscosity breakdown, right? You want your motor oil to be thick enough that when it gets moved around in your engine, it coats the sides of the internal parts of your engine and keeps them lubricated and keeps them from rusting. If the oil loses its viscosity, if it becomes more fluid, it'll just fall to the bottom of whatever part of the engine it's in and it won't do its job. If the motor oil gets too thick, then it's going to cause a lot of resistance in your engine, and that's not good either. But we know some things, like motor oil. When you pour motor oil, it seems thick, right? It pours slowly. Or think about honey. When honey, especially if it's been around for a while, it gets really, really thick. Is it still a liquid? Yeah, but it's really, really thick and it doesn't flow very well. Maple syrup. If you stick it in the fridge, it gets even thicker, right? Corn syrup, molasses, all of these are very viscous liquids. So viscous liquids flow more slowly than liquids that are not viscous. So viscosity, that resistance to flow, is due to stronger intermolecular forces. It's like a bunch of people, maybe people wearing Teflon suits, and they're crowded into a space where they're literally rubbing shoulders with each other. But if you're all wearing Teflon suits, then you're going to just slide past each other, right? If everyone's wearing Velcro, you're going to stick on each other. You can still move, but it's going to require a lot more effort, and the movement of people is going to slow down. Does that make sense? So more viscous, stronger forces. Another way to think of intermolecular forces is stick-togetherness. If they're really sticky, like balls covered with tape or something, they're really sticky, they're not going to move around as well. So I hope you had some lunch and that doesn't make you hungry. But the reason maple syrup pours slowly is because the molecules interact with each other very strongly. And so they don't slide past each other very easily. And that causes it to pour slowly.